Experiment number 5, Thermodynamics, Solubility of Borax. In this experiment, we have multiple goals. The first goal is to determine the solubility of borax. Given its solubility, we can determine the value of KSP. What is KSP? It's the solubility product constant. Given the value of KSP at various temperatures, we can plot the natural logarithm of KSP versus 1 over temperature in Kelvin. And we use this graph to determine the enthalpy and entropy of the dissolution of borax in water. Here's an example of KSP. If we dissolve aluminum sulfate in water, KSP is equal to aluminum 3 plus to the power of 2 times sulfate to the power of 3. Where does this number come from? 2. It's in front of aluminum ion. This number 3 is in front of this sulfate. Experimental design. How do we determine the solubility of borax? Well, first we dissolve solid borax in water at different temperatures. At least we need to do 3 temperatures. So hopefully we can do these 3 temperatures, and if time permits, let's do 1 or 2 more temperatures. What's the chemical reaction? It's here. And what is this? This is borax. This is the chemical formula of borax. And what is this? This is formula for borate. Borax, when you put it in water, it decomposes into sodium plus and borate and water molecules. Alright, so this is the simplified chemical equation. So first we make the solution of borax at different temperatures, and then we decant the solution of borate in a graduate cylinder. We measure its volume, and then we can transfer this solution into a beaker and titrate it with hydrochloric acid. And note that the concentration of borate increases as the water temperature increases. So if we have 3 samples prepared at these 3 temperatures, we'll see more solubility in this solution at a higher temperature, and the least amount of borax dissolved in water at the lowest temperature. Over here we have some numbers. At different temperatures we have different solubility, but those numbers are in mass percentage. So really this 1.99 means we can dissolve 1.99 grams of borax in about 100 grams of aqueous solution. So if you look at this graph, as temperature increases, the solubility increases. How do we determine the value of KSP? Well, first we need to look at this equation. When we look at this equation, this is solid, water is pure liquid. So really we just need to worry about the concentration of sodium plus and the concentration of borate. And fortunately we have this nice equation. The concentration of sodium plus is always 2 times the concentration of borate. So after we write out the expression of KSP, which is sodium plus to the power of 2, again, where does this 2 come from? It comes from this coefficient in front of sodium plus. So sodium plus to the power of 2 times borate, and we know sodium plus is equal to 2 times borate. So we can plug this in here, and then KSP is simply 4 times the concentration of borate to the power of 3. All we need to know is the concentration of borate, alright, in mole per liter or molar. Now if we know the value of KSP at various temperatures, how do we determine the enthalpy and entropy of the dissolution of borax? First, we can write out 2 equations for the standard Gibbs energy of the dissolution of borax. The first equation is delta G is equal to delta H minus T delta S. This knot in superscript denotes the standard state. So we have this equation at temperature T. We have another equation also at temperature T. We have delta G is equal to negative RT times the natural logarithm of Ksp. Both equations are correct at temperature T, so we put equal sign between this and this. Therefore, delta H minus T delta S is equal to negative RT ln Ksp. We rearrange this equation. By dividing both sides by negative RT, we get this equation. Now, the natural logarithm of Ksp is something in red times 1 over T plus something in purple. Alright, so now I want you to imagine the logarithm of Ksp is y. 1 over T is x. So it's y is equal to something times x plus something. This in red is the slope, and this in purple is the intercept of the equation. So again, we'll just tabulate 1 over T. We'll tabulate the natural logarithm of Ksp. We plot the graph. We do a linear regression, and then we can get the slope and the intercept displayed on the graph. And the slope is again in red, negative delta H over R. Therefore, if you have the slope, delta H is simply negative R times slope. The intercept is delta S over R. Therefore, delta S is simply R times the intercept. Again, you make the graph, you do linear regression, you get a linear equation. From the linear equation, you will see the slope and the intercept. The slope times negative R, that will give you the standard enthalpy of dissolution. The intercept times R, that will give you the standard entropy of dissolution. R is the gas constant. Now let's talk about the experimental procedures. First, you need to dissolve solid borax in water at around 50 to 55 degrees Celsius. Dissolve as much as you can to form a saturated solution of borax. And then you decant 5 milliliters of the solution in a graduate cylinder. It would be nice if you can decant exactly 5.00, but that's unnecessary. If you decant 5.2, 4.8, that's fine as well. And then you transfer the solution from the graduate cylinder to a beaker. You can use some DI water to rinse the cylinder and then transfer the rinsing water into the same beaker. And then you cool the solution to 30 to 35 degrees Celsius. Again, decant about 5 milliliters of solution into a cylinder. The reason is we need to measure the volume with this graduated cylinder. Do the transfer, rinse the cylinder, transfer everything into beaker 2. And then cool the solution to about 10 to 15 degrees Celsius. If needed, use some cold water bath to bring the temperature down. If your temperature is slightly above 15 or slightly lower than 10, that's okay. Just record the temperature. And decant about 5 milliliters of the solution into a graduated cylinder and measure the volume to 0.01 milliliters. Alright, this volume is pretty important. And then rinse the cylinder, transfer everything into this beaker number 3. Now you have beaker 1, beaker 2, and beaker 3. They all contain a borate solution to be titrated. We'll use roughly 0.2 molar HCl to titrate these 3 beakers. We always do scout titration first, and then we do more accurate titration. So here I have some estimated numbers. Those are estimated value of HCl needed to titrate those 3 beakers. If you have beaker number 1 that contains solution collected from 50 to 55 degrees Celsius borax solution, well, at this higher temperature we can dissolve more borate. That means we need more HCl to titrate the borate. So roughly 20 to 40. For this temperature we need roughly 8 to 16 milliliters of HCl. For the third sample collected from the lowest temperature borax solution, we have the least amount of borax, and therefore we need the least amount of HCl for titration, about 3 to 6. But again, you need to do a scout titration first, and then perform a more accurate titration. Data analysis. So other than using your own data, you need to obtain more data from your data partner. Again, this is to make sure that we average data from like 2 student groups to hopefully get more accurate result. 1 mole borate reacts with 2 moles of HCl. Therefore, if you know the volume of HCl you used, the concentration of HCl, this will be given to you. And then if you know the volume of borate you decanted from the samples at different temperatures, so it should be roughly 5 milliliters. And then you can calculate the concentration of borate using this equation. The concentration of borate is equal to the volume of HCl, the titrant, the concentration of HCl divided by 2 times the volume of borate. Again, this is the original volume of the borate solution you decanted from the original sample. Okay, again, this number 2 is put in here because 1 mole borate reacts with 2 moles of HCl. Now, if we have the value of the concentration of borate, we use this equation to compute the solubility product constant, KSP. We do this for 3 different temperatures. You'll get 3 different values of KSP at these 3 different temperatures. And then you take the logarithm of KSP, you take the reciprocal of temperature in Kelvin. For example, if temperature is 30 degrees Celsius, you need to convert it to 303.15 Kelvin first, and then you take its reciprocal. So over here, 1 over T has a value of 1 divided by 303.15. You make this graph and do a linear regression. Make sure 1 over T is the horizontal axis, and again, the temperature has to be in Kelvin. So 1 over temperature has to be in reciprocal Kelvin. And then after you do the linear regression, display the linear equation on the same graph, you will get the slope, you will get the intercept. The slope times negative R is equal to the standard enthalpy of dissolution. The intercept times R is the entropy of the dissolution of borax. And then we achieve all those experimental goals.